So let's go back to Coulomb's law. Here is the magnitude of the force between 2 point charges. That's part of Coulomb's law. But what about the direction? Okay. What about the direction of the force? Well, let's take a look at the direction. Direction of F based on symmetry. Again, we use symmetry considerations. Now, let's join a line between two charges, Q1 and Q2, 2 point charges, and we call this vector R. And now, suppose the force given by charge 1 to charge 2 is in a certain direction. Let's say that's the direction, okay? Let's say that's the direction. No, that's F. And that direction makes an angle theta with the line joining the two charges. Okay, I'm going to argue, based on symmetry considerations, that the angle theta must be either 0 degrees or 180 degrees. It cannot be any other value. How do we know that? Well, again, the key idea is symmetry. What is symmetry? Symmetry means the system behaves in such a way that when you do a certain operation, let's say you make a flip or you make you make a rotation or whatever you do, after you do this, you find that whatever you did leaves the system unchanged. Okay? If that happens, we say the system exhibits certain type of symmetry. Okay, for example, if you have a sphere, a uniform sphere, and then when you rotate the sphere about its center, what happens? Nothing, right? Because it's the same uniform sphere that you see. Now, in this case, we have 2 point charges, Q1 and Q2. They have no shape and no size. And there's a certain force between them, right? Now, you can imagine what happens if I were to rotate the system consistently to charge Q1 and Q2 about an axis, which is defined as the line joining Q1 and Q2. All right, so imagine this is the axis, and I'm going to make a turn. I'm going to make a rotation. Now, remember, these are 2 point charges, right? So if you made a rotation, did you really change the system at all? Not really, right? You still have the same 2 point charges, and they still behave the same way. So what do you think? How should the force change when you make a rotation like that? The answer is nothing, right? Nothing should happen because you didn't really change the system. Now, suppose the force initially points this way. Okay. Now, when you make a rotation about this axis, what happens to the force? The force would have to follow you, right? Suppose you turn 30 degrees, the force have to also turn 30 degrees, right? So what if you turned 180 degrees? The force has to flip from this side to that side, which means it is now pointing that way. This angle is also theta, right? After you turn 180 degrees about this axis. But wait a minute, we know that nothing is supposed to happen after you turn 180. The force is to be the same, right? So, what do you think the angle should be? Obviously, these two forces must be the same force. So that leaves theta equal to 0. In fact, theta can also be 180 because, you know, if the force goes like that, right, along that line, you turn, which means that's 180 degrees, right? And you turn about this axis, still nothing happens. So the only possible values for the direction of F that leave the symmetry unaffected is theta equal to 0 or theta equal to 180. That means the force must be along the line connecting these two charges. Okay? It is either in the direction of R or in the direction of negative R. That is the only choice. Otherwise, we violate symmetry considerations. All right. Now, given that we're now able to write down the expression, the vector expression, what we're going to do is we're going to put a vector R here. You need to use a little sharp cap. What does that mean? It means it's a unit vector. Okay? It is a unit vector pointing from Q1 to Q2. Okay, so R is defined as the vector R divided by the length of R itself. So it tells the right direction, okay, tells the right direction, but has a magnitude of 1, so it doesn't really affect the magnitude of this side. Now, does this expression automatically account for the attractive and repulsive nature of electrostatic forces? Well, let's see here. Suppose Q1 and Q2 are both positive or both negative. That means the product of Q1 and Q2 must be what? Must be positive, right? And according to this expression, this whole thing is positive. Okay? This whole thing is positive. That means the force is along the direction of R, which means Q1 gives Q2 a force which is along the direction of R, which means Q1 is repelling Q2. Make sense? Okay? On the other hand, if Q1 and Q2, one of them is positive, the other one is negative, then the product must be what? Must be negative, right? So that means the direction of F is now along negative R, which means Q1 now gives Q2 a force which is that way. That means it is now attracting Q2. Make sense? So this expression automatically accounts for both the positive and negative, in other words, attractive or repulsive nature of the electrostatic forces, depending on the product Q1 times Q2. Okay, now let us do a comparison between the two most fundamental important forces that we have studied. One is the electric force, the other is the gravitational force. Okay, first of all, symmetry. They both have symmetry considerations. For example, here, the force is proportional to Q1, Q2. Here, in the gravitational case, is proportional to what? M1, M2, right? So this is very symmetrical. Now, what about universality? Yes, the gravitational force is universal because everything has mass. As long as you have mass, you can participate in gravitational force. On the other hand, the electric force is not universal because not everything has a charge. So that is wrong. Okay, dependency on R, as we have seen before, both happens to have the same 1 over R squared dependency. Again, we don't know why, but we will learn in the next chapter how special this dependency is. Unlike any other power, r to the negative 2 is unlike any other power. Okay, now what about the constants here? This guy has a constant g, which is 6.67 times 10 to the negative what? 11, right? SI units. But this guy has a very large constant, about 8.9, about 9 times 10 to the what? Positive 9. Okay, about 9 billion SI units. So that tells you there is a huge discrepancy in the magnitudes of the electric force and the gravitational force. Okay, the gravitational force is usually very weak unless M1, M2, at least one of them is astronomical, because you have to multiply everything by a very, very small constant g, which is about 6 to 7 parts in a trillion. Okay, very, very small. That tells you the gravitational force usually is not very important unless we're dealing with astronomical masses such as the Earth, the Sun, and so on. On the other hand, electric force is much, much greater. Even for regular size charges like 1 or 2 coulombs, the force between them can be very, very large. So that's something we keep in mind. Okay, another thing is positive and negative. Yeah, the electric force, as you know, can both be positive and negative, which means attractive or repulsive. The gravitational force is always attractive. Okay, always attractive. So we use a negative sign for attractive force because the force points along the negative R direction towards each other, right? Okay. Responsibility. In other words, what is that force responsible for? We learned from Physics 1B that the gravitational force is what's responsible for holding the universe together, right? Why does the Earth go around the Sun? What's the force responsible for that? That's gravitational force. The Moon goes around the Earth, right? We stick to the surface of the Earth. All these things are because of the gravitational force. Again, the gravitational force is usually quite weak. The force between you and I, for example, gravitationally is virtually zero. But when it comes to astronomical matters such as the Earth, the Moon, and the Sun, the solar system, the Milky Way, that sort of thing, the mass can be tremendous that the gravitational force becomes the dominant force. Okay, so the gravitational force is the dominant force in the universe when it comes to large scale, astronomical scale objects. On the other hand, what's holding everything else together? For example, what's holding the atoms of this pen together? What's holding the atoms or molecules of our body together? What's holding the molecules of this table together? Well, you cannot think of gravitational force for that trick because it's too weak, right? It's not strong enough. So, who is responsible for that? That will be the electric force. Okay, so electric force is what's responsible for holding atoms together in a solid and even in a liquid. Without electric forces, these atoms will not stick together, they will fly apart. You will never see solids or liquids. Okay, so that is a simple comparison between electric and the gravitational forces. Okay, now we're going to look at our first example involving electrostatic force. In this setup, we have a massless string attached to a point mass at the end, and on that side is an identical massless string attached to an identical point mass. Okay, each charge also has a mass m, same thing, and the length of each string is L. Now, imagine if you put these two strings, suspend them at the same point, then at the end, these two charges will repel each other, so they're not going to hang vertically downwards like that. Rather, they're going to push each other away like this, right? And suppose you find that the angle between the vertical line and each string is theta. Can you find the charge on each of these point charges? This is a very simple example involving a combination of electric force and the gravitational force. We know that when they reach equilibrium, the net force on each charge will be zero. And this is totally symmetrical between these two charges, so I don't have to consider both charges. Let's just consider one of them. Okay, now let us identify the forces on each charge, on this particular charge. One of them is, of course, the gravitational force. That is mg, downwards, right? Another force is the tension, T, in the string. Anything else? Well, if these are the only two forces, the net force is not zero, it's not going to balance, right? Obviously, there is another force between this charge and that charge. And that force is repulsive because these two charges have the same sign, right? It's repulsive, and it is pointing that way, horizontally. All right, and this is the electric force, F of E. Now, obviously, these three forces, T, F of E, and mg have to add up to zero. The question is, how do we find the charge Q? Okay, now all we have to do really is to make sure the net force add up to zero, and we can do so both vertically and horizontally. This angle is also theta, as you know. Okay, so in the vertical direction, what can we say? Well, there is an mg going down, and there's a t cosine theta going up, right? F of E has no vertical component. So in the vertical direction, we write t cosine theta, and that is the force going up, must equal to mg, right? Must equal to mg, okay? That's how we balance the vertical force. Horizontally, there is a force going this way, that's a component of T. There's also another force going the opposite direction, and that is the electrostatic force. They must cancel each other out. Okay, so let's write down the expression for the horizontal component of T, and that will be T sine theta, right? Now, it has to equal to F of E. Okay, how much is F of E equal to now? Coulomb's law. Okay, Coulomb's law. Ke times what? Q1, Q2, they're both equal to Q, so that's just Q squared. Divided by what? The distance squared. Okay, now the distance from here to there, we call it A, so that's 2A, right? That's 2A. Okay, squared. There we go. So, vertical net force equal to 0, horizontal net force equal to 0, right? I must make sure to calculate Q, and the way I do that is by first eliminating what? T. How do I do that? What's the simplest thing to do? Well, I can take this equation divided by that equation, right? So T is gone. So you get sine over cosine. What's that? That would be tangent theta, right? And the other side, take this divided by that. What do I get? I get KE Q squared over 4 A squared. I factored out, and then mg. Okay. Now the only thing I do not know yet is A. But A we know equals to, what is equal to? L times, this is A, this is L. So A equals L times sine theta. Right? There we go. You plug that in, okay? And then you get an expression for Q squared. Okay, so Q squared equals to tangent theta times what? 4 mg. And then A squared. A squared is L sine theta and then squared. The whole thing divided by KE. Okay? Now, after that, you just take the square root of both sides, and there we go. We find Q. Right? So this is a very simple example concerning the balance of electric force and the gravitational force. Okay. So far, we have only studied electric force between 2 point charges. But in reality, oftentimes we're dealing with charges that are not really like points. Rather, they have, maybe you can have one charge, maybe you can have a continuation of charges, say a uniformly charged sphere, that sort of thing. So what do? Well, to extend our discussion beyond 2 point charges, we must invoke the so-called the principle of linear superposition. Let's see what it means. Now suppose I have 2 charges, 1 and 2. What's the force between them? We know that's Coulomb's law, right? You know, the force is like this. Say suppose they're repulsive, the force is like this. That's F1 to 2. Now, what if there is a third charge present? Okay, charge number 3 here. And with that new charge here, my question is, what is the net force on charge 2 from both of these charges together? Well, this is when the so-called principle of linear superposition comes in. It says that you can think of the total force on object 2 as if these 2 charges act on it totally independently without regards to the presence of the other one. So for example, suppose charge 3 were not present at all, then charge 1 would give charge 2 a force like this, right? And now suppose charge 1 were not present at all, only charge 3 were present, and then that charge 3 would then give charge 2 a force like that, okay? We call it F3 to 2, right? And then the principle further says that the actual force on charge 2 is really just the linear summation, vector summation of these 2 forces. So in other words, it's like that. Like that. That is the actual force on charge 2. Now this all sounds very simple, and some of you might think that, you know, this is, of course, what else is there, right? I mean, it's supposed to be the way it is. Well, in reality, the principle of linear superposition is not all that simple to understand, because it is entirely conceivable that when you introduce a third charge, okay, charge 3, it is entirely conceivable that the force between 1 and 2 could change, right? The fact that it didn't is not something that we can take for granted. For example, let's use a human example, for example. Suppose you and I are having a certain conversation, a confidential conversation, okay? And all of a sudden, a third person comes in, and what happens? We don't want this guy to hear what we say, so we change our topic, right? So that means that in the presence of third charge, it is entirely possible for F12 itself to change. Of course, if that really happened, that would make our job really difficult. Well, fortunately, nature is not that complicated. Choose to take the simplest way, and that is, regardless of how many charges are present, the forces remain the same. All you have to do really is to add them all up linearly. Okay, that is the principle of linear superposition, and that is the principle we are going to use to extend our discussion of electric forces beyond that between 2 point charges.